In this physics tutorial, you will learn 1. What are significant figures? 2. How to find the number of significant figures in a given numerical value. 3. How to round up a number to the required number of significant figures. 4. Why are significant figures so important in measurements? Introduction. The flying distance from London to Birmingham is about 101 miles, or 163 kilometers. Can we say 101.000 miles or 163.000 kilometers to be more precise? Why? The weight of an African bush elephant is about 6,000 kilograms. Can we say, elephant's weight is 6,000.000 kilograms to be more precise? Why? The dimensions of a door are 194 centimeters times 87 centimeters. Can we round up the result and say to the carpenter to produce a door with dimensions 2 meters times 1 meter? Why? What are significant figures? Let's start this section by giving answer to the above questions. Thus, for the flying distance from London to Birmingham, we cannot round the result further as it is already rounded. Therefore, it is meaningless to say 163.000 kilometers when 163 kilometers is a rounded value. Also, we cannot round the elephant mass more than to the nearest kg as it is obvious the original value, 6,000 kilograms, is already rounded. Finally, we cannot round up the dimensions of the door to the nearest meter and order the carpenter to produce a 2 meters 1 meter door because it will not fit to the wall. From the above examples, it is obvious that the numerical information must be meaningful and it must help the reader understand the point. In physics problems, we use significant digits or figures to express the answers. Significant figures represent the accuracy with which we know the values. The accuracy of an apparatus is equal to the smallest unit it can measure. For example, the accuracy of a ruler is 1 millimeter, as it represents the smallest division of the ruler. The accuracy of an electronic balance is 1 gram, as it shows the smallest value above 0 appearing in the screen, and so on. Thus, for example, if there are 3 tiles in each 1 meter of a room, and we are interested to know the length of a tile, it is obvious we divide 100 centimeters by 3. However, the calculator displays the value as shown on screen. The first decimal place represents millimeters, the second 1/10 of millimeters, and so on. But is it really meaningful to write the result with such an accuracy? Of course not. First of all, we measure the length of the room using a meter stick, a ruler, or something similar. The precision of these devices extends up to millimeters. Hence, it is meaningless if we express a result in a higher order of accuracy than the precision provided by the apparatus itself. We can either say 33 centimeters, or 33.3 centimeters, for the length of a single tile. 33.3 centimeters is the best version, but 33 centimeters is also acceptable considering the fact that the gaps between the tiles can contribute in the decrease of the actual value. But it is wrong to say 33.33 centimeters, as the apparatus offers a precision up to 0.1 centimeters, 1 millimeter, so the result must not contain more than 1 decimal place. If we want to express the above-mentioned result as 33 centimeters, it contains 2 significant figures, 2 threes, and if you express the result as 33.3 centimeters, it has 3 significant figures, 3 threes. Example 1. Round up the results of the measurements shown below to meaningful values and then write the number of significant figure each value contains after making the corrections. 1. The distance between 2 cities A and B is 364.000 kilometers. 2. The dimensions of a notebook measured using a simple ruler are 35.425 centimeters and 24.1 centimeters. Solution 1. As stated before, it is meaningless to express the distance between 2 cities at a higher order of accuracy than kilometers, as often it is not clear where a certain city begins or ends. Therefore, we must write simply 364 kilometers for the distance between cities A and B. In this case, the result is expressed in 3 significant figures, 3, 6 and 4. Since the accuracy of the second measurement is up to 1/10 of a centimeter, or up to 1 millimeter, it is meaningless to consider the hundredths and thousandths of centimeter in the first measurement. Therefore, We can write 35.4 centimeters for the first measurement or dimension, and 24.1 centimeters for the second one. Both numbers have three significant figures each, 3, 5 and 4 for the first, and 2, 4 and 1 for the second measurement. How to find the number of significant figures in a given numerical value. There are 5 basic rules to find the correct number of significant figures in a given numerical value obtained during a measurement. They are as shown on screen. 1. The zeros at the end of a whole number are not counted. For example, in the value 7,800 kilograms, there are only 2 significant figures, 7 and 8. This is because zeros here act simply as placeholders. They are not meaningful digits. They are written in the measurement result only to show that the measurement value contains 78 hundredths of kilogram, not 78 kilograms or 7.8 kilograms. 2. Zeros at the beginning of a decimal number are not counted. For example, if during a measurement the result of speed is 0.000945 kilometers per second, the number of significant figures in this number is 3, those being 9, 4 and 5, because the other digits, zeros, act again as placeholders. We can write 0.000945 kilometers per second as 0.945 meters per second. The last number indicates that we have a speed of 945 thousandths of a meter per second. However, we can also say, the speed is equal to 945 millionths of a kilometer per second, and in both cases we are correct. Therefore, only 9, 4 and 5 are meaningful in this value. 3. All zeros between two non-zero digits are always counted. For example, we are allowed to write the measurement value 0.003705 quintals as 0.3705 kilograms or 370.5 grams, but we cannot write it as 0.00375 quintals, 0.375 kilograms or 375 grams, because these values are not equal to the original one. 4. All zeros at the end of a decimal are always counted. It is because zeros at the end of a decimal indicate a higher degree of accuracy compared to cases in which we don't write them at all. For example, in physics the value 3.200 meters is not the same as 3.2 meters, because the first shows that the measurement is taken using a device divided into millimeter, while the other number, 3.2 meters, shows that the measurement is less accurate. Either it has been measured using an apparatus divided into dm, or the result is rounded up to the nearest dm after the measurement was taken. 5. If the measurement value is written in standard form, scientific notation, only the numerical part before the powers of 10 is counted. The exponential part is not considered. For example, if the result of the speed measurement taken during the observation of a meteorite shows the value 3.507 times 10 to the power of 4 meters per second, the number of significant figures in this result is 4, those being 3, 5, 0 and 7. This is because this result can also be written as 35,070 meters per second, and from the first rule of significant figures, it is obvious the 0 at the end is not counted. It simply acts as a placeholder. On the other hand, all the other digits are counted because if you remove one of them, the result is not the same as the original anymore. Example 2. The dimensions of a room are 5.4 meters times 4.27 meters. Calculate the surface area of the room by expressing the result in the correct number of significant figures. Solution 2. The room sides are measured with different levels of accuracy. The smallest division of the apparatus when measuring the length was 0.1 meters, 1 decimeter, while for the width it was 0.01 meters, 1 centimeter. Therefore, we must use the level of accuracy of the less accurate measurement to be sure. It is better rounding up a dimension to a less accurate value and be sure your result is close to the correct value than working in vain with numbers that probably are not correct. In other words, it is better to write the width as 4.3 meters, by rounding up the value to the nearest tenth of meter, instead of 4.30 meters. This is because we are not sure whether its exact value was 4.25 meters, 4.26 meters or 4.34 meters, as all these numbers become 4.3 meters when rounded to the nearest tenth of meter. Therefore, the surface area of the room is The accuracy of the result is 0.01 meters squared, or 1 decimeter squared. Given that length and width are expressed in tenths of meter, this is a value that complies with the desired order of accuracy, because 1 divided by 10 times 1 divided by 10 equals 1 divided by 100, which equals 0.01. Therefore, there are 4 significant figures in the result. The first 2 figures, 2 and 4, show its whole part, square meters, and the other 2 figures, 5 and 1, represent the tenths and hundredths of square meter respectively. How to round up a number to the required number of significant figures. Suppose you measure the perimeter of a regular hexagon, and obtain the result p equals 25.0 centimeters. The question requires you to calculate the side length of the hexagon. Thus, you make the following calculation. It is obvious you cannot write the result in this way. You must round the result to fit the apparatus you have used to take the measurements. From the perimeter value, you can see the accuracy of apparatus is up to 0.1 centimeters. This number has only 1 decimal place. Therefore, you must write the result at 1 decimal place as well. Hence, either you will write it as 4.1 centimeters or 4.2 centimeters. In this case, you must use the rounding rules, i.e. when the last digit is greater than 4, we have an increase in the rounded value. In this specific case, the last digit is 7, so we must write 4.2 centimeters, for the size of the hexagon's side length. Why are significant figures so important in measurements? From what we said above, it is clear that 5.700 kilograms is not the same thing as 5.7 kilograms. The first number has 4 significant figures. It is measured more accurately than the second one. Indeed, the second value can be a number ranging from 5.650 kilograms to 5.749 kilograms. All these numbers when rounded to 1 decimal place give 5.7 kilograms. This is not the case of the first number. It cannot be neither 5.699, nor 5.701, but exactly 5.700 kilograms. Its accuracy is 1 gram, while the accuracy of 5.7 kilograms is 0.1 kilograms, or 100 grams. Although in mathematics these two numbers are equal, in physics they are different because they are obtained by using apparatuses with different degree of accuracy. Summary. Significant figures represent the accuracy with which we know the values of a measurement. The accuracy of an apparatus is equal to the smallest unit it can measure. There are 5 basic rules to find the correct number of significant figures in a given numerical value obtained during a measurement. They are as follow. Point 1. The zeros at the end of a whole number are not counted. 2. Zeros at the beginning of a decimal number are not counted. 3. All zeros between 2 non-zero digits are always counted. 4. All zeros at the end of a decimal are always counted. 5. If the measurement value is written in standard form, only the numerical part before the powers of 10 is counted. The exponential part is not considered. If we have a combined measurement, for example we have the length and width given and want to calculate the area, first we must write both numbers at the same degree of accuracy, to the accuracy of the least accurate dimension, and then doing the operations.